Today we're going to look at factoring. Hopefully this is, again, a little bit of review for everybody. So first off, factor can kind of take on two different meanings. So factor in the verb form is to write a quantity as an equivalent product. And then factor as a noun is an individual component of a product. So you'll hear us say factor maybe in different situations, and one could be a verb, one could be a noun. Okay, so we are going to take a look at factoring each of the following integers completely. So in other words, a different way to say this would be, let's write them as the product of only prime numbers. Okay, so I can think to myself, 12 could really be 3 times 4. 4 is not a prime number, but I could break 4 up into the product of 2 times 2. So that would be an example of prime factorization. Same thing with 36. 36, we could break this up a couple of ways. I'm thinking probably 6 times 6. They are not prime numbers, so now I need to break each of these guys up. Okay, so 6 can be broken up into 2 times 3. Same thing over here, that could be broken up into 2 times 3. So if I'm looking at this as your prime factorization, it would be 2 times 2 times 3 times 3. Notice if I were to multiply this, I would still get 36. Same thing back here. If I were to multiply 3 times 2 times 2, I'd get 12. So I'm changing the way they look, but I'm not changing the value. Okay, we're going to take a look at some more. So we're going to rewrite each of the binomials, meaning two terms, as a product of an integer with a different binomial. So in other words, I'm going to try and pull out a common factor or a common term. So if I'm looking at these first two, I'm saying what's in common with 5x and 10? Well, they each have a factor of 5 in them. Okay, so now I have to find that binomial. So 5 times what gets me 5x? It's x. 5 times what gets me positive 10? And that would be 2. So here is my integer and my binomial. Okay, we'll try that again with this next one. So something in common with 6x and 15, they each have a factor of 3. So now I say 3 times what gets me 6x? That would be 2x. 3 times what gets me 15? And that would be 5. Okay, same thing over here, even though I know maybe it looks like it's backwards from what we're comfortable with, works the same way. Something in common with 6 and negative 14x. I could pull out a 2 from each of those. So then I think 2 times what gets me 6? That's 3. Now watch your signs here. 2 times what gets you negative 14x? So it needs to be a negative 7 and an x. Okay, so that is referred to as factoring out. You heard me say that on all of those. And we're factoring out the greatest common factor. Could be numbers, could be variables, could be both. So the next one that we're looking at, same idea. It's just that when we're going to write our product, that term that we're pulling out is probably going to be consisting of both numbers and letters, or numbers and variables. So in this first one, finding a common factor, finding what's in common with both of these terms. They each have a factor of 3, and they each have a factor of x. So now I ask the same question. 3x times what gets me 3x squared? Well, I already have the 3, right? So 3 times 1 gets me 3. X times x gets me x squared. So again, same thing. 3 times what gets me 6? That's 2. X times what gets me x? That's a 1. And remember, we don't have to write ones. Okay, same idea here. I want to see what's in common with both of these terms. I could pull out both 5 and an x. So now let's start with the constants. So 5 times what gets me 20? So that's a 4. X times what gets me x? And that's 1. Don't have to write the 1. Okay, so now I do the same thing. 5 times what gets me negative 5? So that's a negative 1. X times what gets me x squared? And that has to be x. Because remember, when you're multiplying variables, you're adding exponents. Okay, last one here. What is in common with both 30 and 20? Well, they each have a value of 10. And notice only the first term has an x, not the second term. So I can't pull out an x here. Okay, so 10 times what gets me 30x squared? So 10 times 3x squared would get me 30x squared. Okay, same thing here. 10 times what gets me negative 20? So 10 times negative 2 would get me negative 20. Okay, let's try one more. So same thing. I want to see what's in common, both numbers and variables. So between 20 and 36, they each have a factor of 4. X squared and x, I could pull out at least an x. Okay, so now we have to think. Let's do the numbers first. So 4 times what gets me 20, so 4 times 5. X times what gets me x squared, so that's an x. 4 times what gets me negative 36, so that's a negative 9. X times what gets me x, and that's 1. So again, we don't have to write the 1. Okay, so those were binomials meaning 2 terms. Now we're on to trinomials meaning 3 terms. And they can also be factored. And we are going to, it says, rewrite each of the following as the product of its GCF and another trinomial, meaning I'm going to pull out some term that's common, and then I'm going to have a 3-number term that it's being multiplied by. So if I'm looking for what's in common with all of these terms, I could see a 2 is in common with all of these terms. I can't say x because notice this last term does not have an x value. So if I pull out a 2, now we just have to do that same thing that we did on the other questions, but I have 3 terms to do this over. So 2 times what gets me 2x squared. So 2 times 1 gets me 2, but then I also have this x squared. Okay, 2 times what gets me 8x. So 2 times 4x would get me 8x. And for this last one, 2 times what gets me 10? 2 times 5 gets you 10. So there is your GCF, and there's your trinomial. Okay, next one. So now I'm noticing each of the terms have an x. So I know I can pull out an x. And each of the terms look like they're going to be divisible by 4. So I could pull out a 4, and I could pull out an x. Okay, so 4 times what gets me 8? That's 2. X times what gets me x cubed? That's x squared, because remember, when you're multiplying variables, add exponents. Okay, 4 times what gets you negative 12? So that's a negative 3. X times what gets you x squared? And that's an x. And our last one, 4 times what gets you negative 20? I'm sorry, that's a positive 20, so positive 5. And then x times what gets you x? Oh, that's 1. So I don't have to do anything with the x. I don't have to write down a 1. Okay, our next term. So again, I have 6x cubed, 15x squared, 21x. They all have an x. So I can pull out at least an x. And then when I'm thinking, how about numbers in common? I could pull out a 3. A 3 is divisible by all of those. So 3 times, or 3x times what gets me 6x cubed. So 3 times 2 gets me the 6. X times x squared gets me x cubed. Okay, next, 3x times what gets me 15x squared. So 3 times 5 gets me the 15. X times x gets me x squared. And our last one, 3x times what gets me negative 21x. So 3 times a negative 7 gets me the 21. And again, x times 1, I don't have to write that, is equal to x. Okay, so now we get into something called conjugate multiplication. Notice when you're looking at that conjugate pattern, a couple of things that we see here. Notice both terms are squared. Notice we have a subtraction. That's huge. It has to be subtraction, otherwise this does not work. And then notice what your factors turn out to be. It looks like both of them will have the same numbers, but different signs. Okay, so that would be called the difference of perfect squares. So when we're looking at that pattern, let's see if we can pull that out below. So we're trying to find the following binomials as a product of a conjugate pair. Okay, so here's that form that we have up above. This is our x squared minus a. So we get our 2 factors, where I'm going to have, now I have to think to myself, what 2 numbers I could multiply by itself to get me 9. So I know 3 times 3, same term, would give me 9. Okay, so over here, x times x would give me x squared. Then all we have is 1 is positive, 1 is negative. Okay, same idea here. So we see that it's a difference. I see that these two are both perfect squares. 4 is a perfect square, x is a perfect square. So perfect square meaning if I square rooted 4, I should get 2 and 2. If I square root x squared, I get x and x. And now I just have to think 1 is negative, 1 is positive. Same thing over here. Difference of perfect squares. So 4 is a perfect squared, x squared is a perfect squared, 25 is a perfect square. So if I square root all of these, square root of 4 is 2. Square root of x squared is x. Square root of 25 is 5. 1 is negative, 1 is positive. And the last term here again, all perfect squares. So if I square root 16, we get 4. If I square root 81, we get 9. And if I square root x squared, we get x. Sandwich them with a plus and a minus. So we just factored all of those. So same idea here, it's just now we have some fractions. Okay, so they work the same way, don't worry. And we're going to start with 1/4. So if I were to take the square root of a fraction, I would square root the top and square root the bottom. Okay, so square rooting x squared, we get x and x. If I square root 1, we get 1. If I square root 4, we get 2. Same thing over here, 1 and 2. Plus, minus, you factor it out. Okay, we try it again. So again, 25 is a perfect square, 9 is a perfect square, x squared is a perfect square, and I see the minus sign. So the square root of 25, I get 5. Square root of x squared, I get x. And then for my denominator, square root of 9, we get 3. 1 is plus, 1 is minus. Now we have two variables. Guess what? It works the same way. Because again, all of these are perfect squares, and I see a subtraction. So we're just going to square root each of these terms. So square root of 36 is 6. Square root of x is x. Sorry, square root of x squared is x. Square root of 49. So I have to think what times what gets you 49? That's 7. And the square root of y squared is y. 1 is plus, 1 is minus. So now we're going to look at a combination of GCFs and different perfect squares, and we're going to try and put this all together and see what we can do. Okay. First thing is always want to consider factoring out the GCF. You can find that first, always pull that out, it makes your factoring much easier. So for this first term, I know they each have a 5, so I'm going to pull out the 5. And what I have left is x squared minus 4. Now I see here is like what we had up above, difference of perfect squares. So I'm going to have x plus 2, x minus 2, square rooting both the x squared and the negative 4. Okay. Again, starting with b, pull out that GCF first. So I can see 7, it's going to come out of this term first. So that would leave me with 4x squared minus 1. Okay, now this is the same thing that we had up above. 1 is a perfect square. 1 times 1 gets you 1. These are both perfect squares, so I can keep going. Square root of 4 is 2. Square root of x squared is x. Square root of 1 is 1. And then we have a minus and a plus. Okay. Common with 40 and 250 is 10. So I have 4 minus 25 x squared. And both of these, all of these are perfect squares, so if I keep going, I'm going to have square root of 4 is 2. Square root of 25 is 5. Square root of x squared is x. 1 is minus, 1 is plus. Okay, they look scary, but if you follow these patterns, they work out pretty well. Lastly, pull out the GCF. Now notice what we have on both of them. Not only could I pull out a 3, but I could also pull out an x. Okay, so a little difference. I pull out a 3 and an x. And what do we have left? So we're going to have x squared. And then over here, we're going to have minus 16. Okay, still going to both be the difference of perfect squares. So again, I can continue my factoring. So square root of x squared is x, square root of 16 is 4, make it a plus, make it a minus. Okay. Hope that helps. Bring your questions to class and we will answer them. Hope you guys have a great day.